Hello dear students. So in last lecture we were talking about electric field intensity due to a line charge. So at the last of the lecture I gave you one assignment to find electric field due to a finite line charge. So let us have a look towards that. So let us take our XYZ coordinate system. Okay, now take a finite line charge. Let us display a finite line charge, and we need to calculate electric field at a point P. Okay, so this line charge extends from z is equal to minus L by 2 to z is equal to L by 2. So here also we need to add all the differential charges, means the electric field of all the differential charges on point P. So let us take a differential charge. Let us say this is differential charge, and we need to calculate electric field at this point P. Okay, so let us say this point P is at rho 90 degree and 0. Okay, and this differential element is at 0, 90 degree and Z. Okay, so same thing we need to do, and we will reach to a point where we can write the electric field, the differential electric field as to be differential electric field at point P. So now we can write here the charge itself. So this is rho L dl divided by 4 pi epsilon rho square sz square under root whole square. Okay, and your dr length is rho a rho minus z az. Okay, now if you take the dl length in the minus z direction, so you will see that this az quantity will eliminate it, and what we will get, we will get let us say d integral at point P will be equal to 0 to L by 2. Just see, the limits are just changing. First we were integrating from 0 to infinity. Now we are integrating from 0 to L by 2. So this will become 2. 2 will come out because there is symmetry around the xy plane. So it will be rho L dl rho A rho divided by 4 pi epsilon rho square plus z square 3 by 2. And from here what we did, we put z equal to rho cot theta. Okay, then from here you get dz equal to minus rho cosec square theta d theta, and your limit will be at z equal to 0, your theta will be pi by 2, and at z equal to L by 2, what will be your theta? Your theta will be cot inverse L by 2 rho. Just check it. Okay, so solving like before, you will get your EP as to be uh, rho L cos of cot inverse L by 2 rho divided by 2 pi epsilon rho. In which direction this will be? This will be zero direction. So we can just see that this cost will be maximum 1. Okay, so any angle if we take, it means this cost term will be less than 1. So your EP will be less for a finite length line charge. For infinite length, this will become 1, and it will come rho L upon 2 pi epsilon rho. But for a finite length, this will be your electric field. Okay, so after doing line charges, we can also go for surface charge density. So let us find electric field intensity. Electric field intensity due to surface charge. Surface charge distribution. Okay. So here we can come to figure. Okay, let us say this is what x axis, y axis, z axis, and let us say the plane, the surface is on the xy plane. So this is your surface. Now what we will do, we will take a small surface length, small surface area. Okay, we'll call it ds, and ds is placed at rho length, and the angle is phi. Okay, and we need to calculate the electric field at a point P here. which is placed at 0, 0, z. Okay, so now we need to calculate the electric field due to this surface charge density. So let us just draw this uh, distance vector. So here the distance vector will be like this. So let us say this is R1. Okay, R1 P. So P is the final position, 1 is the initial position. So we can write our R1P. So what will be our vector R1P? So your vector R1P will be final position vector minus initial position vector. Final position is our P point and initial position is our the surface charge density. So so this could be written as Z Az minus rho A rho. This phi term may be cancelled out as we have done in the previous derivation for line charge derivation. We can take this P as to be at phi angle. So this phi will be cancelled out. Why we are doing this? Because if you see phi is not, if we change phi, your magnitude of R1P will not change. R1P is the distance between P and your surface differential surface. So this will not change. If you take phi as to be here, then also you will see this R1P will not change. That's why we have cancelled out this phi by taking the P at the phi angle itself. So your mod of R1P will become Z square plus rho square root 2. So now we can easily write our electric field equation at P point. So what will be our electric field? And this will be dE because this is due to the differential surface. So this surface charge is having a surface charge density of rho s. So dP will be dQ upon 4 pi epsilon z square plus rho square root ka whole square, and in which direction? In the direction of unit vector R1P. So we can write unit vector R1P. So this is Z minus rho A rho divided by Z square plus rho square 3 by 2. So we can write this expanding our dq. So dep will become rho s ds upon 4 pi epsilon rho square plus z square 3 by 2 towards rho a rho or z is it I feel. This is, yes, this is z is it. So this is z is it minus rho a rho. Now just see here one very important thing. We can write a rho as to be cos phi ax plus sin phi ax Sine phi ay. Now we can change this cylindrical coordinate system into spherical coordinate system, into cylindrical coordinate system, and we know how to convert that. If phi is the angle, if the phi is the angle, so we can easily derive this point. Okay, so arrow will be xax. So this will be rho cos phi. Sorry, this will be rho cos phi. Mm, oh, doesn't matter. So uh, if arrow is the unit vector, arrow is the unit vector in this direction. If this is arrow, then we can just split in ax and ay direction. We have done this earlier, so there will be no row component because this is a unit vector, so this will also be a unit vector. Okay, so fine. Arrow can be written as cos phi ax plus sin phi ay. Fine. Now just consider a small differential surface just opposite to this surface ds1. Let us say this is ds1 and this is ds2. So this surface will also extend some electric field on this P point. So as this ds1 was doing, so we can take this as to be like this. Okay, then we can write this as to be r2p. So you understand very well that the final vector of r2p will be, so how we can write r2p. So can we write r2p? How you can write it? Final vector minus initial vector. So final position vector is not changing; it is same. So this az will come out to be same, and this initial vector is also rho. It is also rho. Now rho is what, the radial direction. Okay, it is the radial direction. Just one thing is changing, that is the phi angle. This phi angle is changing. Now this ds1 is at this phi angle. So what is this? This is just pi plus phi. This is pi plus phi. Phi is this and pi is this. So this ds2 is placed at pi plus phi angle. So if we want to write this arrow component for S2 surface, then what that will be? That will be cos pi plus phi. No? So angle is now pi plus phi. So this will be ax plus sine pi plus phi into ay. So we know cos pi plus phi is minus cos phi, and sine pi plus phi is minus sine phi. No? So we can see this uh, a rho s1, unit vector a rho s1 and unit vector a rho s2 are just opposite to each other. Okay, so what will happen, this rho component will be cancelled out. This term will be cancelled out when we take the effect of both differential surface, which are placed just opposite to each other. So adding this ep, what will happen, this rho a rho component will become 0. this arrow component will become Z. So we can write our EP now as to be DEP as to be just taking the AZ component. So it will be rho S ds upon 4 pi epsilon rho square plus Z square 3 by 2 Z AZ. So we are cancelling our arrow component. Why we are cancelling our arrow component? Because when we consider uh, all the differential surface on this plane, then we are seeing that all the radial component of the electric field is being cancelled by each other. Okay, that's why we have taken our DEP as to be just in Z direction. Okay, so from here now we can integrate this DEP. So this DEP could be integrated, and this part can also be integrated. So this is rho s. So we can take rho s ds upon 4 pi epsilon rho square plus z square 3 by 2. Okay, and where we will integrate? We will integrate on the surface. And one more component is there, which is z a z. Okay, so now here we need to expand this ds. What is this ds? So to look into ds, we need to just redraw that figure where we considered our differential element. So this is your x, this is y, and this is z. So we are taking a small ds here. Okay. Now see, this ds is made of two parts. It is made as we are talking in cylindrical coordinate system. So this will be made with two dimensions. So it is very much obvious that this surface is not made of this z dimension. Z dimension is above this xy plane. This is in x. This surface is in xy plane. So the two dimension which will be working in making this ds will be rho. One is rho and one is phi. So these are the two dimensions that is making this surface. So in rho direction, this is having what? How much? This is just d rho. No, in rho direction it is displaced with d rho, and in phi direction, how much this has changed? This has changed by this much arc. So I'm talking about this arc. So this arc. So this arc. I'm talking about this arc. So how much this arc is? So we know that this arc length, if this is r and this is phi, so this arc length will be r times phi. So how much this has displaced? This has displaced in phi angle by d phi, a small angle d phi. Okay, and what is the radius? Radius is rho. So how much this arc is? This arc is uh, rho d phi. It is similar to like this is d phi. Okay, up to here it is phi, and here it is d phi. So we this will be d phi into r. Okay, so one is the arc angle. So this is the arc angle, and this is the d rho component. So two dimension will make the surface. So our surface will be our surface area can be written as one is rho d phi, and another is d rho. Okay, so you need to once more look into it how we are calculating the this differential surface area. So uh, this ds is rho d phi d rho. So we can put here so d our d ep will be what? This is rho s, and rho is the radial distance. D phi d rho z az divided by 4 pi epsilon rho square plus z square 3 by 2. Okay, so this is a simple integration. uh, we have got two components d phi and d rho. So the d phi we have to take the whole plane. So uh, so d phi will subtend from 0 degree to 2 pi, because we have to make the full circle, full region we have to cover. And rho we will take from 0 to infinity, because it is infinitely spread. So our rho will extend from 0 to infinity, and our d phi, our phi will extend from 0 to 2 pi. So as we can see, the this quantity, this whole quantity is only having one d phi. So d phi will be directly integrated. So we can write ep, the electric field at point p, has to be d phi will be directly integrated in 2 pi, and we can take the 4 pi epsilon out of this integral, 4 pi epsilon, and then remaining part will be rho s, rho z d rho, and I feel there is two rows. Okay, rho d rho z rho s. Okay, and this will be in az direction. So this is rho square plus z square 3 by 2. This is very simple integration. Uh, so we will just take our rho square has to be t. So this will be 2 rho d rho is equal to dt. Now putting rho d rho has to be dt by 2. So from here rho d rho will be dt by 2. So and for if rho is 0, for rho is 0, t will also be 0, and for rho is equal to infinity, t will also be infinity. Infinity whole square is infinity. So we will change the limits and write our d e. So this is 2 pi upon 4 pi epsilon, and integral from 0 to infinity, rho s will be remaining same, and rho d rho will become, z is also there, rho d rho become dt by 2, and this will be in az direction. Okay, so this will be rho square, that is t plus z square 3 by 2. So integrating this, what we will get, here 2 pi upon 4 pi will be cancelled out, it will be 2 epsilon. Then if we go on integrating this, then this will be z rho s, uh, this upon 2, and 3 by 2, this will come to be minus 2, 1 upon t plus z square. Please check it once. You will see there is no error as such. This 2 and 2 will be cancelled out, and the thing will be, this will be z rho s upon 2 epsilon naught epsilon. When we put our t as to be infinity, this is minus sign will come out. When we take t as to be infinity, then this will become 0, and when we take t is equal to 0, then this will become 1 by z. So ultimately, what you will get? You will get rho s upon 2 epsilon, and in which direction? Az direction. So we can write it separately. Your EP, electric field due to surface charge density, will be what it will be? It will be rho s upon 2 epsilon, and this will be in Az direction. This is the electric field due to surface charge density at point P. So here you can see that this electric field only depends upon the surface charge density. It doesn't depend how close you are to the infinite plane, and so uh, here I will end my today's lecture, and I want to give you some assignment for your next class, which will be next Wednesday. So on Wednesday you will submit an assignment that I will post today. Okay, so be tuned, and thank you. If there are any doubts, you can raise that in the classroom, and soon I will start taking live lectures. But this is it for today. So good day.